Hello. Today we're going to talk about moment of inertia. So moment of inertia, it's also called rotational inertia. And the symbol is I. And the unit is kg from the mass and then meter squared. So we're considering a rigid body like this. It's made up of n pieces of masses. So m1, m2, and there are more of them. So there are n of them. And how do we compute this moment of inertia? So you look at m1, you look at the distance from m1 to this axle. And then you would take the r1 squared times the m1. And then you add this m2, and then the r2 is from the m2 to the axle's distance. And that will be m2 r2 squared. And it kept on doing that for all the n particles. When you add them all together, that's called the moment of inertia. So what does that mean? It's a measure of how difficult, the difficulty that you can turn this mass here, this rich body here. So it's having to do with this is important, having to do with the mass distribution. So the key word is distribution. Yeah. In Chinese, this is called 质量分布. And the distance, right? So where is your mass, right? So like this is everywhere here in the disk. But like here, the mass is only at the outer edge. So you distribute your mass, right, further away from your axle. So having to do with distribution and the distance to this axle, which is the R1 and R2. And so axle is the axis of rotation. And so all the masses rotate around this line here. This is the line. So this one doesn't move, right? But it turns, right? It turns. So you have an angular velocity here, omega. Okay. So the larger the I, the harder to rotate. Okay. The larger the I, the harder to rotate. So it's how difficult that you can. So the larger the I, the harder to rotate. So what are the example of moment inertia? So we'll consider some geometry here. So first one, a disk. So something like this. So if you know the radius is r, you know the total mass is m. Then after some integration, so you do integration. So somebody did it for you. And that results is 1/2 times the mass of the disk times the radius from the axis of rotation. And it's from this point to the radius. So that's the I for the disk. For the sphere, or like a ball, then the R is still the R, the radius of this entire sphere, and M is the mass of the entire sphere. Then it's 2 divided by 5, so slightly smaller than a disk if they have the same mass and the same radius. Okay? And that's for obvious reason, but we don't get into that right now. And ring is I equal to mr squared, so it's basically a 1. So it's even bigger than the disk. It's double of that. And also for a very obvious reason, but we don't want to get into that right now, but it's all the mass is concentrated outside, you see? Right? So that's the mass distribution part. Okay? The key word here is distribution. How do you distribute your mass? Right? Right? So if all the masses is away from the axle, then you have a larger I. Okay? So we're going to give you an example. And I'm going to clear that. And let's do an example. So let's say if you have XO here, and then you had one mass like that, you have another mass like this, okay? And this is massless, okay? This this support here, you can call that a little rod or something, but very skinny. This M, let's call that M, and this one here, let's call that 2M, okay? And let's say this one here is R equal to 1 meter. And this side here is also R equal to 1 meter, okay? And that's equal to 1 kilogram. So for this XO, let's compute the I for this two mass system, right? So your system is equal to M plus 2M, okay? And now it's looking for the I for the system with respect to the XO, right? And this XO, we can call that PP, to XO PP. Okay, so how do we do that? So we do I, right, for the system, it's equal to M, right? This M here times 1, right? Times R, right? So R squared plus 2M, right? 2M times R squared. It's also R, right? So then this is equal to 3mR squared. So then that's equal to 3 times 1 times 1 squared. So that's equal to 3 kilogram meter squared. And that's how you find it. Okay? All right. So we're going to stop here, and until next time. Bye-bye.